Let's go over some code for working with images with OpenCV. OpenCV is a Python library, and the CV stands for computer vision. And OpenCV has some really amazing capabilities that will enable you to do a lot of computer vision. So you can find a lot of information about OpenCV here in this notebook. Well, some of the things that we'll do are simple, things like reading and displaying an image. We're also going to do things that we've done before with the PIL library, like extracting the RGB values, the amount of red, green, and blue in a particular pixel. But we're also going to do other things, adjusting brightness and contrast and Gaussian blurring. These are things that we'll talk about soon. So you can see here some descriptions of the functions that we'll use here. ImRead, that's short for image read. ImShow, that's image show. And then ImWrite, image write. And we can find the shape of the image here with this shape attribute. We can resize with this particular method here. We can do different conversions. And there are all sorts of things you can do. Instead of looking at all this text, let's dive into the code and see how it works and what happens. So what I want to do is I want to start with going over how to install OpenCV. And so this is if you're working on a local machine, or in other words, if you're working on your own laptop. It's possible that you've never installed OpenCV before. If so, you should run both of these lines in your notebook. You should delete this comment, this hash sign or pound sign here, delete that, and just run the rest of this line starting with the exclamation point where it says pip install. That will install OpenCV on the machine that you're using. In this case, in this notebook, OpenCV has already been installed, so we don't need to run these. After you've installed OpenCV, in this case, we are going to mount our drive, and this tells the notebook where it needs to look for files. In this case, it's going to look for files in a particular Google Drive location. And after you've installed OpenCV, you might want to check which version you're using. In this case, we're using version 4.1.2. Now, many aspects of computer vision are quite complicated and complex. And so sometimes someone will send you some code, some OpenCV code, and it works really great for them and it doesn't work for you. And the reason might be that they're using a different version of OpenCV than the one you're using. And that can lead to a lot of confusion. So if you're collaborating with people or sharing code, it's helpful to make sure you're using the same version of OpenCV. So this is the version we're using here. And let's talk about reading and displaying images. Well, we're going to start by importing some important modules and libraries. So we import these here. And we specify that we want to draw our plots in line. That means here in our notebook, instead of writing them to a file or writing them somewhere else, we want the plots and images to appear right here in the notebook. That's why we do matplotlib inline. After that, we use the imread method of OpenCV. So we use cv2.imread, and we open this JPEG image that we have. And then it's very simple. We can use imshow to show the image. So there's the image. Now, let's keep going. There are some important things you need to remember about OpenCV. Now, OpenCV was made by some creators and some authors, and they're people we don't know, and they can do whatever they want with their library. They can create their library however they want, and they can set whatever defaults they want. And one really interesting default in OpenCV is that they expect your images to be in what's called a BGR color scheme. So far we've talked about RGB images, where we specify how much red is in a pixel, how much green, and then how much blue. Well, BGR is the same thing, but it's just in a different order. Here we specify how much blue is in a pixel, then how much green, and then how much red. So you can imagine that this can lead to some confusion. If we read an RGB image, but we think it's a BGR image, we might end up displaying it wrong. And in fact, that's exactly what happens here. When we use the imshow method from matplotlib, it expects a different format of image, and you can see it seems to have gotten sort of the red and the blue mixed up. And so, yeah, this potentially can cause some real problems. And so you have to be very careful about which particular functions you're using, which libraries you're using, and what format they expect their images to be read in. So be very, very careful about that. So here is a summary of these differences. OpenCV is going to use BGR. Matplotlib is going to use RGB. So as long as you're aware of that and can make adjustments for that, you should be just fine. Let's talk about some image manipulation we can do. One thing we can do is we can resize images. So for example, if we want to take our original image and make it have a width of 400 and a height of 400. You can see we've specified this width and height that we want here. And we've created this new variable called dimensions. This dimensions variable is what's called a tuple. It's just a collection of these two numbers, width and height. And once we've done that, it's very easy. We can use this resize method, cv2.resize. And then we just say which image we want to resize and which dimensions we want it to have. And then we save this as our new image. And that's our new image. And so you can see what we're going to print out is two different shapes. We're going to print out the original shape of our image and the new shape of our image after resizing. In both cases, we're going to use the shape attribute to calculate that and then display it. Finally, we can show our new image here. And you can see it's displayed here where you can see we've converted it to be like a square instead of a rectangle like it was before. And well, this is one way to resize an image. However, we may want to be a little more careful as we're resizing images so that we can preserve, high resolution. So let me tell you what I mean. If you're making an image bigger, you may want to create new pixels in that image. So for example, let's say you have a white pixel that's right next to a red pixel. If you make this image much larger, these pixels will then be separated from each other. So when you resize an image to make it larger, the pixels are all going to spread out. But we don't want to display an image that has all these spread out pixels with nothing in between. We want to put something in between these pixels as they've spread out. And that's why we can do this thing called interpolation. Interpolation is going to make educated guesses for what should be in between pixels as an image is spread out or as an image is resized to be larger. For example, if we have a white pixel and a red pixel, they spread out as the image resizes. And what do we put in between? Well, we may put some pink pixels in between because pink is sort of in between white and red. And that's what interpolation is. Interpolation is making that educated guess for what pixels should be in between existing pixels so that we have sort of a better look and a better resolution when we resize. And so in this case, we've said that we want to do interpolation. And there's this method of interpolation called linear interpolation, and that's what we've specified that we want to use here. So we're using the same method, the resize method, and we're creating our new image just like we did before. The only difference is that we've done interpolation to improve the quality of our final image. And so you can see when we print it out, it's a little bit hard to see where it's happened because the resizing has been a little bit minor. But in fact, every time pixels are too far spread out after this resizing, OpenCV has interpolated, or it's made an educated guess for which pixels and what color the pixel should be in between those spread out pixels. So let's keep going. Well, when we resize, we may want to make sure we avoid changing the look of an image. So for example, if we start out with a rectangular image, if we resize so that the rectangle has a very, very different shape, if it changes from being a short, wide rectangle and becomes a tall, thin rectangle, that could make the image look distorted. It could make a duck look like it's like a tall, skinny duck instead of a broad duck. And so we want to avoid that. And one of the easiest ways to do that is to use what's called a scaling factor. So for example, if you want to take the original image and make a new image that's 40% of the size of the original image, what we can do here is we can define this scale factor and say 0.4, in other words, 40%. And we can say the new height and new width we want is going to be the original height times this scale factor. So 40% of the original height and 40% of the original width. And when we calculate these dimensions, well, we're going to say, okay, it's going to be a tuple, or a collection of these two numbers, the new width and the new height. Then we resize according to these dimensions. We do interpolation again. And you can see this new image, it's much smaller. It has a width that's 40% of the original and a height that's 40% of the original. In other words, it's been scaled with that scaling factor. Great. So next we can do color conversion. And this is something we did a little bit with the PIL library, but we can also do it here. So one function that we'll be interested in is this function called CVT color. And so we can create it here. We can say, well, let's use this CVT color method, and we're going to take our image and do a conversion. That's what CVT is supposed to be short for, convert color. And what kind of conversion are we going to do? Well, we're going to convert BGR to gray. So we take our BGR image, the original image, convert it to grayscale, or in other words, black and white. It does the conversion for us, and when we show it, we can see that now we have this grayscale image. So remember, RGB is not the only way to store images, nor is BGR. There's this other type of channel called an HSV channel, or an HSV format. So here we can convert our color image to an HSV image. And we use this convert method again, but we use a different converter. This is BGR to HSV. That converts our images to HSV images. And when we show it, it looks a little strange. And, well, so why would we ever want to do this? Or why would we ever want to show this image? Well, there could be a few reasons. One reason is HSV has high performance in certain computer vision tasks. So some types of object recognition, if there's poor lighting in an image, and you need to detect, is this a dog or a cat, or is this a person's face who I know? Sometimes HSV can get better performance, so sometimes conversion to HSV can lead you to more success with these advanced computer vision tasks. So that would be one reason why you might do HSV conversion. We can also adjust the brightness and contrast of images. And again, this is something that we don't have to do manually, but OpenCV provides some very helpful capabilities for us to do that. And so here, what we're going to do is we're going to define this function here. This is a user-defined function. And basically, we're going to change two things. We're going to change contrast, and we're going to change brightness. And, well, you can see in some bullet points here, it talks about contrast and brightness. So contrast is defined as the differences between light and dark areas of the picture. So if you make dark areas darker and light areas lighter, suddenly this image is going to have much more contrast. If you do the opposite, an image is going to have less contrast. And people who, photographers and people who work with images are sometimes interested in adjusting that at least slightly to get a better look, the look that they want. And we do the same thing with brightness. We can, well, that's a little bit simpler. That's a matter of manipulating pixel values. You, for example, on a grayscale image, you just choose higher numbers for the pixel values and it gets closer to white. And, we do a similar thing with RGB. And so remember, we're doing this not just for fun and not just to display images, but we're getting ready to do some really advanced tasks like object detection and image segmentation. These are like machine learning tasks. And so adjusting contrast and brightness can sometimes give us better performance in these advanced machine learning tasks. And so here's this function that we looked at where we're going to control the contrast and brightness of our image with these alpha and beta variables. And the way we do it is by using this method, convert scale abs, and that will adjust both of those things or either of them for us. So let's talk about these values. Alpha is supposed to be between 1 and 3, and it's used to control contrast. Brightness is supposed to be between 0 and 100. That's the beta value. It controls brightness. So here, for example, what we're doing is we're saying, I want to take my original image and I want to create a new image from it. And the new image, I want to have these different parameters. I want it to have 1 for alpha and 50 for beta. And you can see that this is supposed to be an image with increased brightness because we've gone up to 50, which is a relatively high brightness value. And so you can see here's our original image. Here's this image with increased brightness, judging by this high beta value here. And so we can also do the same thing by adjusting the contrast. And here we need to adjust the alpha parameter to make it higher. We make it a 2, and the brightness parameter we don't adjust. And so here you can see that here's our original image, here's the image with increased contrast, so bigger differences between the light and dark parts of the image. Now, there are other things you might want to do to images. One type of thing you might want to do is Gaussian blurring. Well, Gaussian blurring is a way where we take an original image. Let's look at the outcome first before we look at the code. We take an image and, to put it simply, we make the image blurrier. And so these are examples of the original image after applying blurring. And, if you've never thought about blurring, think about what it is. What does it mean for an image to be blurry? Well, we have an intuitive sense of it. We can just look at images and say that's a blurry image, that's not a blurry image. But what is it actually? Let's look at this original image. And so, for example, there's this kind of dark, maybe green part of this duck's head. And it's next to this kind of white part of the duck's head. And you can see there's like a pretty strict contrast there, where we have a dark pixel right next to a brighter or a whiter pixel. And if you look in the blurred image, what's the difference? The difference is that we don't have sharp edges anymore. Blurring is essentially the removal of sharp edges. So instead of a dark pixel right next to a white pixel, what we have is a very dark pixel here, and then slightly wider, slightly wider, slightly wider, and then, we finally get to white pixels here. So we get this kind of transition between dark and light instead of sharp edges. And the way we can accomplish this is by what's called filtering, where we say, okay, when you draw this pixel, don't just draw the value of this pixel alone, draw the value of this pixel combined with the values of the pixels around it. So instead of just drawing a green pixel right here at this green point on the duck's head, we say take that green pixel and combine it with some white, combine it with some other things all around. And so every pixel you see is actually a combination of it and all the pixels that are in its neighborhood. That's what blurring is from a technical point of view. We don't need to know much of that right now. We can just use this method, Gaussian blur. So we say, okay, I want to blur my image. K size means how much of that neighborhood around the image do we want to look at when we blur the image, or in other words, when we combine a pixel with all of its neighbors. So 5 means we want to combine each pixel with its neighbors that are up to 5 pixels away. Here we're saying pixels that are up to 15 apart from each other are going to be combined to make our blurred image. And so you can see by choosing a different K size or kernel size, you can see we get different types of blur or different amounts of blur. And so OpenCV does all of this for you. The reason it's called Gaussian is because it's using a Gaussian function, or in other words, a bell curve, to decide how much of each neighbor pixel to combine with the original pixel. And we don't need to worry too much about that now. We can just notice that this method will do all of that work for us. We can show our image and show the results of this Gaussian blur. So this is how you blur images. There are also ways to deblur images. That's a little bit harder, but we can try that another time. So remember, when we're working with images, we're thinking of images as multidimensional arrays. These are all the pixels of the image, but we represent each of the images, each of the pixels, by numbers. So maybe since we're using BGR, we could say that this is the amount of blue in a pixel, this is the amount of G in a pixel, or green in the pixel, and this is the amount of red in the pixel. And so we have these 3 channels for every single pixel. And we have this for, all the columns of our array, or in other words, all the columns of our image. And then we have this whole row of all these different columns. And altogether, it's our full image matrix with all these numbers that specify what every single pixel should look like. So this is our image matrix with it's not the full image matrix. It has these ellipses here that show that we're omitting parts of it. So finally, we can look here and we can say, we can use this shape attribute to determine the size of our image. And well, here we're using size, the size attribute to determine size, and the shape attribute to determine shape. And if we're working with a grayscale version of it, then we can use those same attributes but with that different version to see how it differs. And you can see the shape of our original image is this. This is the width and height with 3 channels. The grayscale image only has 1 channel. It's just 229 and 320. That's just the width and the height. And so when you multiply these things together, you get the total number of elements in our full image matrix. For the color image matrix, it's quite a large number. For the grayscale image matrix, it's a smaller number. And so these are important things to remember. Every time you work with an image, remember you're working with a matrix that looks like this, and you can check its shape and its size using these attributes. So the last part of our code is about region of interest. And so what if you're only interested in a particular part of your image, or a particular region called the region of interest? And remember, the image is stored or represented as a matrix. And so taking a part of the image is the same as taking a part of the matrix. And we just need to decide which part of the matrix we're interested in. And in this case, we say, here's our image, and we want row 30 through 200, column 50 through 300. And so, we can see that this is essentially cropping. It's cropping the outside of the image. Remember, when we started with our original image, we had quite a lot of water all around the duck on the outside. But by cropping those outsides, by saying we just want the middle rows and the middle columns, we've extracted just this particular region of the image, and we can show it here and see which part we've extracted. And that could be helpful as well if we don't want to use the full image for our machine learning algorithm. For example, we just want to use the middle of it. This can help us really easily access just the parts of the image that we want. So this has been an introduction to OpenCV in Python, and I hope you have a great time with OpenCV, and I wish you happy learning.